When a national team scores during the World Cup, the collective emotional release is deafening. Millions of fans are entirely focused on the pitch. But miles away from the stadium, engineers in windowless rooms are monitoring an entirely different high-stakes situation. They are the operators at the National Energy System Operator, or NESO, responsible for managing the national power grid. Their challenge stems from a specific cultural habit. When a football match pauses, millions of people simultaneously stand up and boil water. A typical high-powered UK electric kettle draws nearly 3,000 watts. Multiplying that single high-draw appliance by a massive television audience creates an instantaneous demand shock on the power network. This phenomenon is known as the TV pickup. This represents the heartbeat of the UK electrical grid. The network must maintain a steady 50 Hz, the boundary where electricity supply perfectly matches national demand. When demand spikes, the physical strain of millions of kettles switching on simultaneously drags the frequency downward. If frequency drops too far, protective systems automatically sever connections to prevent hardware damage. This causes a cascading failure, plunging cities into darkness in seconds. The threat begins with a lull. Just before kickoff, there is a drop in electricity usage, the kickoff deviation, as spectators settle down and turn off other household appliances to watch the broadcast. For the engineers, this initial drop marks the start of a 45-minute countdown toward a guaranteed energy shock the moment the first half ends. The exact second the referee blows the halftime whistle, millions of fans leave their sofas to make hot beverages or open refrigerators. This creates an immediate impact on the grid. Within minutes, the network must absorb a surge of demand that often exceeds hundreds of megawatts. Traditional baseload power sources cannot react quickly enough. A nuclear plant takes days to adjust its output, and even a responsive natural gas plant requires several minutes to spin up to full capacity. To manage the gap, grid operators literally watch the match. By observing the broadcast in real time, they can identify the precise moment of a halftime whistle or a final penalty kick and initiate power dispatch sequences seconds before the kettles are switched on. Maintaining grid stability requires pairing this human anticipation with specialized technological assets that can respond to demand in seconds rather than minutes. The first responders are grid-scale battery systems. These installations can inject power into the network in milliseconds to stabilize frequency transients. For larger, sustained surges, the grid relies on pumped storage hydro facilities, massive reservoirs hidden inside mountains. Instructive. This works by releasing water from an upper reservoir. Gravity forces the volume down a central tunnel, rapidly spinning turbines to generate electricity before the water enters a lower lock. These facilities are designed for speed. Plants like Croatian can go from standby to maximum generation in under 30 seconds. This combination of battery systems and gravitational water release provides the necessary bridge to meet the demand spike until slower thermal plants can be synchronized to the network. The most difficult scenario for grid stability occurs when a knockout match goes into unscripted extra time or a penalty shootout. Because the exact minute of the match conclusion is impossible to predict, operators cannot schedule thermal generation beforehand. Instead, they must hold fast reserve assets on standby, waiting for a sudden, massive spike in viewership and demand. The record for this kind of surge occurred during the 1990 World Cup semifinal between England and West Germany. After a penalty shootout, the grid faced a 2,800 megawatt demand spike, the equivalent of over 1 million kettles being switched on at once. While digital streaming has reduced the impact of routine television pickups, live international sports finals remain highly synchronized. They are the ultimate stress test for national infrastructure. Managing these spikes today is different than in 1990, as the grid transitions away from fossil fuel reliance toward a low-carbon model. The modern grid uses a mix of renewable integration, vast battery networks, and demand flexibility, where smart devices or industrial users temporarily reduce consumption to balance the load. While millions of fans are caught up in synchronized cheering and tea-making, a sequence of technical responses is unfolding across the network to hold the frequency steady. Ultimately, these shared cultural moments are made possible by the rapid coordination of kinetic and chemical energy across a national grid. Every time the lights stay on during a final, it is the result of engineering that anticipates the pulse of the nation.